Okay, I suppose we'll get started. First, I have to apologize for clearing my throat a lot. I'm not contagious. It's not a cough. It's not actually a cough. I don't know what's wrong yet. I need an ultrasound on this area to see what's wrong. So I don't know, whatever. But point is, I'll be probably clearing my throat, coughing a lot. But you don't have to worry about me getting you sick. Okay. Last class we didn't actually do too much. It was a short day. I just kind of gave a demo on the software that you needed to use for the assignment, and also quickly showed off Wolfram Alpha. And then I just did sort of a quick example of just the set theory stuff that we were doing, just so that everyone was on the same page, and then there was a quiz. Right? It was nothing too fancy. With that, I suppose we might as well just move on. So today, at least for most of the day, it might take up the whole day. We might briefly introduce the next topic. I guess we'll see how it goes. So I want to take a brief foray into recursion. So I'm going to approach it from a bit more of a mathematical perspective, because while it's something that comes up a lot in programming, it is also very mathematical in nature. A lot of algorithms are defined recursively. A lot of mathematical results are defined recursively. So just as the word recursion means something that refers to itself. So, you've probably heard, people will say things recursively where you're like, what does that word mean? And then they use the word and the meaning of the word, and you're like, that didn't help me at all, actually. So that's an example of recursion. Not useful recursion, of course, but I'm going to cover some mathematical examples, and then in the next unit, we're going to cover some examples that actually have a lot of application in programming. So for now, let's just actually start with the definition. So this is in terms of mathematical sense and also in programming. A recursive function is a function that refers to itself in its definition. So an example in programming would be you write a function, and then inside that function it calls itself with different arguments, or a variable amount of arguments, but that's the idea. And in mathematics, it's kind of the same concept. We do exactly the same thing. So just as a side note on recursion, from a programming perspective, recursive algorithms are often inefficient in some way, be that time inefficiency, space inefficiency, some other kind of inefficiency, but they're usually really easy to implement in the sense of code work. Oftentimes recursive algorithms, since it's something that calls itself, you do a little bit of work and then call yourself again, right? And then the stack inside your programming language or your computer is what handles the most of the work, right? It builds a stack and then unfolds itself in a specific order. Now, because of that, we ideally would like to avoid them, because while they're easy to implement, they are inefficient and they are a nightmare to debug, because by their definition, they're a function that refers to itself. So where did it go wrong? Well, good luck, right? Because even if you use, I don't remember what the thing in VS Code is, the debug tool that lets you sort of step into an algorithm. Well, if you step into a recursive function, it's just going to step into itself a bunch of times, and it's going to be really hard to figure out what's going wrong. So it's really, really hard to debug. But on the flip side, lots of real-world algorithms and applications and definitions are given to you recursively. So you're sitting there and you're trying to tackle a business problem, and your boss said, okay, we'll solve this problem, and it's probably defined recursively, right? It'll be like, okay, you have this problem, do a bunch of this work, and then in this process you have shrunk the work down, so now redo that work on the shrunken problem, right? That's a recursive definition that you can run into in the real world. So something important is to unpack that definition and turn it into something efficient code-wise, because you don't want to write inefficient code unless you have some ridiculous time constraint. And one thing to note is recursion is never necessary because of von Neumann machines. So every computer programming language any recursive algorithm can be forced to be an iterative algorithm. Whether or not that's a useful thing to do is a different question, because that will probably come with a lot of complexity, right? You just might not be able to unpack it into something useful. The opposite is not true. Just if something's iterative, you might not be able to make it recursive. So that's another thing to note is, it's sometimes the difficulty is being presented with a recursive algorithm. And you're like, okay, well, if I do this recursively, it takes, say, on the order of minutes to run, which in your application is way too slow. But then if you unpack it and figure out what it's really doing and find an iterative solution to it, it does it in seconds, right? So then you save a lot of time. So that can happen, right? And you'll save memory because you don't have a stack anymore. So for the purposes of this unit, though, there are lots of things I'm going to define that have non-recursive definitions that are the ones you want to use. But for the purposes of explanation, we're going to use the recursive definitions. So the first one that I want to go over is the idea of the factorial, which is a very common mathematical function. So the factorial of a natural number n is, so it's n exclamation mark. You've maybe seen this on your calculator. You've probably had to use it when doing probability and combinatorics. So that NCR thing, if you had to do that manually or on a sheet of paper, you use this function. So all this is you take the number n and multiply it with every number that precedes it. So n times n minus 1 times n minus 2 times n minus 3 and so on until you get down to 1. So this is n times n minus 1 times n minus 2 ... times 3 times 2 times 1, right? You just multiply all those numbers together, and that's what the factorial is. There is a little side note here because we said natural numbers include 0 for our purposes because computing it's nice to start at 0. What is 0 factorial? Because that doesn't fit into this definition, right? We should probably define what this is. For a lot of deeper mathematical reasons related to the Riemann zeta function, we say it's 0, or 0 factorial is 1. And this works out not just because of that deeper reason, but because in terms of algorithms that we do in math or formulas, this is what we want, right? It actually makes sense mathematically as well. So this is both convention and justified in other ways. So I guess you could think of it as what is the result of repeatedly multiplying nothing? We just say it's 1, right? You might say, well, why isn't it 0? Again, Riemann zeta function, and because of algorithms that we care about. This is sort of related to, this is something that in prime numbers, everyone's like, okay, the definition for a prime number that everyone kind of intuitively knows is it's a number that is, its only divisors are 1 and itself. So every smartass is like, well, why isn't 1 prime? Because 1, its only divisors are 1 and itself. And it's like, okay, well, explaining why would explode your brain, because the reason why is because we said so. There is not some deeper mathematical justification for it. The reason why is because if 1 were prime, then every algorithm that has to do with prime numbers doesn't work anymore. Because if I said, okay, prime decomposition, you can uniquely factor any integer into a product of prime numbers uniquely. If we say 1 is a prime number, that means 1 to the power n, where n can be anything, is another unique way of factorizing that number. So now you can't factor numbers uniquely anymore because 1 is a prime. So then that means that theorem would require you to say, okay, well, suppose 1 is not prime. And then that means every definition ever says let p be a prime that's not 1. And now you have a problem. So why is 1 not a prime number? Because our life is easier if it's not. So that's the reason why. Same thing here. Why is 0 factorial equal to 1 even though it kind of doesn't really make sense? Because we said so. Because we are the arbiter of the rules when it comes to some of this mathematical stuff, and it just turns out that that's what ends up working for everything. For, again, deeper reasons. But we'll get into prime numbers later on. So one thing to note here is this unit is on this recursive idea, and this definition here is not a function that refers to itself, right? It's just n times n minus 1 times n minus 2 and so on. This is a function, right? It's saying if you have a number n, say 5, it's 5 times 3, 4 times 3 times 2 times 1. Yeah?
So, this is probably going to sound stupid. So, if you're doing n minus 1 and then n minus 2 and you keep going,
yeah.
so you're eventually going to hit n minus 43.
Sure.
How do you get to 3, 2, 1?
Because, well, what is 47 minus 43? 4 times 3 times 2 times 1. Yeah, so you just, you take the number that you're at, and then just the number preceding it, multiply it, and then before that, and then before that, and before that, until you get to 1, basically. So you know, 1 factorial is 1, 2 factorial is 2 times 1, 3 is 3 times 2 times 1, 4 is 4 times 3 times 2 times 1, and so on, yeah. And the recursive definition might actually make it a little, well, I'm going to say it's going to make it clear as mud, I guess, which is usually what recursion does. So we can redefine this. It's going to give the same result, but it'll be defined recursively. So let's define the factorial. We're going to call it now, so I'm choosing this notation so that it matches, you know, programming, as the following. So in a recursive definition, there's sort of 2 parts here. The first one is what we would call the termination case, or the end case, or the base case. Because what is going to happen with a recursive function is we are going to shrink the problem down until we get to some really, really simple case that we already know how to solve. So what we're going to say is, let's take a look at this. So if we look over here and we say, what's 1 factorial? Well, it's 1, right? So, okay, that seems like the easiest case, right? So if we say fac of 1 is just 1, right? We're done. So now we need what's called the recursive part. So this is what I would call the base case or terminating case, either one. There's no, I don't think, any consistent wording for it. So now we also need another part of this definition, which we call the recursive case, and that's, okay, it's not 1, what do we do? Right? What are we going to do? Well, if we're looking for a recursive definition, it's a function that refers to itself. So that means we're going to say, okay, we're going to take n, and now we need to reduce the size of our problem while also referring to itself. So what we can do is we can say, all right, well, take the factorial of instead n minus 1 and multiply that with n. Because that's really what we're doing, right? We're saying, okay, n times the factorial of n minus 1. N times n minus 1 factorial. Right? And so this is called the recursive case. And I like, again, this is a pretty mundane example of recursion, but it lets us sort of explore it a bit more, right? Because we can compare, you know, this definition with this definition and sort of play around with it, right? And see that they're the same, first of all, but also just, you know, get comfortable with recursion. So let's just actually compute some factorials here. So using both definitions, so n is equal to 1, well, that's the base case, so that's trivial over there. Using this definition, fac of 1, we know it's 1, right? Because either what we're plugging into this function is 1 or it's not. If it's 1, then we know the answer, it's 1. If it's not 1, then we use this definition. So you if you really wanted to include it, you would just say fac of 0 is equal to 1 also. So now let's look at this definition. So this one is not defined recursively, so we're just going to say what's 1 exclamation mark. Well, we look at this definition here, right? It's this number times all preceding numbers. Well, so that's 1 times everything that's before 1, which there's nothing, right? It's just 1 times, that's it. Okay, cool. All right, what about n equals 2? So 2 factorial, this is, well, again, it's start at 2 and times everything preceding it, so it's 2. What about this definition over here? So fac of 2. So this is where we now have to look at this recursive definition, right? It's going to say, hey, it's not 1, so we need to do this, which is this number times that number minus 1, right? So it's going to be 2 times the factorial of 2 minus 1. I'm writing it out very explicitly, but you could do it in your head, of course. So this is 2 times fac of 1, which we know is 1. So that's 2. All right, so they agree, right? So this is kind of the idea with recursive functions, and this is actually exactly how your computer unpacks them, right? It says, okay, you asked for, let's do n equals 5 as an example. So over here, this is easy. The definition says start at 5 and multiply it by every preceding number. 5 times 4 times 3 times 2 times 1 is 120. In factorials, he's kind of memorizing them. So what about here? So this is fac of 5. We're not in that case of 1. We're in the case of something that's not 1, so we have to use the recursive step, which says, okay, take 5 times the factorial of 5 minus 1, right? This is our n. So I'm actually going to color it in so it's easier to see. Right, so that's the thing that we're plugging in, right? So this is 5 times the factorial of 4. And so now we need to repeat, right? Now we need to figure out what is the factorial of 4. Well, your computer would go, okay, well, I'm going to go figure out, what is this? It's 4 times the factorial of 4 minus 1. Right, and so on and so forth, right? So this is 5 times 4 times the factorial of 3. And I'm hoping you see the pattern here, right? Then it's going to be 5 times 4 times 3 times the factorial of 2. And that's going to be 5 times 4 times 3 times 2 times the factorial of 1, which is 5 times 4 times 3 times 2 times 1, which is the same thing, right? So, okay, these definitions match, of course. But the interesting thing here is just sort of seeing how your computer would behave when it deals with a recursive algorithm, right? It's going to say, okay, I've seen the function call. In order to figure out factorial of 5, I need to know what factorial of 4 is. So then I will go figure out what factorial of 4 is. I need to know the factorial of 3, and so on and so forth. And then it gets to the bottom, and now it says, oh, okay, factorial of 1. I know how to solve that problem. It's just 1. Right? So then it will say, okay, this is 1, which means we go back to here. This is 2 times 1. This is 3 times 1, and so on, right? So that's sort of how it will do it. It'll build the stack like that. So again, this is a very simple example of a recursive function because, I mean, we probably wouldn't define it recursively when we're doing it because there's just such an easy closed form solution of it, right? It's just a loop, right? Just, you know, start at n and then do n times, multiply into that n minus I, where I starts at 1 and goes through the loop, right? And that would give you a non-recursive definition of the factorial. But the point here is also, I mentioned that you can take any recursive definition and write it iteratively. Well, this is another example, right? Recursion, iterative. But that's a pretty trivial example. So how would we write this in code? Well, exactly. This is why recursion is nice, because it's already done for you, right? The algorithm writes the code for you, right? So in Python, as an example, how would we actually write this? Well, I know it's a little uncomfortable to sort of write code on a whiteboard. Sorry, it's in the notes if you want to see it. So we're going to define a function to be the factorial of n. Pretty standard. So if n is 1, then we do our base case, right? We're going to return 1. So this right here is our base case. Otherwise, what are we going to do? We're just going to do the recursive case. So we're going to return the factorial, n times the factorial of n minus 1. And so this is our recursive case. And so you can kind of see what's happening here, right? You call it with 5, and it says, okay, well, n is not 1, so we're in here. So I return 5 times calling the function itself again with 4 instead, and so on, right? Now, a lot of the examples I can talk about, the problem shrinks in a very obvious and natural way. So what I mean by that is the number got smaller, right? It got reduced by 1. But sometimes unintuitively, your problem can get smaller by getting bigger, right? The point of a recursion, it has to make the problem smaller. You have to get closer to whatever ends your problem, right? So in this case, our goal is to eventually get to plugging in 1, right? Once we plug in 1, we know that the algorithm is going to terminate, right? It's going to stop. So if you instead just don't have this, then your algorithm is just never going to stop. It's going to run forever, right? So this termination case is important. Well, 1, it stops your algorithm, but 2, it tells you what conditions shrink the problem, right? Our goal is to get to 1, so we want to shrink our number. If your goal was to say when the set or the data type I have is completely full, then your base case would be, okay, it's full, do this thing. Then that means your recursive step would actually be making the set bigger, right? You start with an empty set and you want to get to a full set, then making the problem smaller is actually adding stuff to the set. So that would be sort of an inverse example of sometimes recursion gets smaller in non-obvious ways. So anyway, if you just do that in Python, you can get the factorial, right? I mean, again, this is a kind of bad way to implement it. Generally speaking, recursion you should try to avoid it where possible. Yeah.
So you're saying in the bottom left corner that's how a program would unpack it?
Well, kind of and kind of not, because the stat gets really weird. So what's going to happen is if you call this with if you call fac of 5, what it's going to do is it's going to go here and it's going to say, okay, we're going to return 5 times fac of 4, but we can't finish this until we get fac of 4. So then it will say, okay, well now I need to do this. So it's going to say this is 4 times fac of 3. So there's sort of a 2-step process here, right? It's going to sort of go deep into the recursion. It's going to build the stack. So then this would be 3 times, I'm just going to call it f in this case. And then this would be 2 times f of 1, which we know is 1, right? But now it's going to reverse it and say, okay, this is 1, so this is 2 times 1, so I'm going to return 2, right? And now I go up here, and I'm say, that's what this is. So this was 2, so it's 3 times 2 is 6. Aha. Now I know the result of this. So now it's 4 times 6, which is 24. Aha. Now I know the answer to this, which is 5 times 24, which is 120. And now that's what we wanted, right? So it's going to sort of do this, it's building what's called a stack of calls to this function, and then it will unpack it with the result individually.
Yeah, why doesn't it just look at it
Because computers can't look ahead, right? It doesn't. So this is why recursion is inefficient, because your computer, well, okay, let me put an asterisk there. Modern programming languages are sometimes smart enough to detect simple recursion at runtime. So this right here, it probably detects and goes, that's a really simple recursion. I know how to replace that with a non-recursive algorithm. But like really complicated stuff, or even stuff that's not complicated that we're going to talk about, like so binary search tree algorithms, your computer would look at it and say, okay, I don't know what's coming ahead until I resolve this, right? So it has to build this tree here. And especially when we start talking, I'm going to give examples that are a little bit more complicated where you can actually build a tree of the function calls, and then you work your way back up, and then that's how it figures it out. So yeah, some of them it can look ahead, and you can, an example that I'm going to give is not factorial, it's a Fibonacci sequence, where you could do that recursively. It's a terrible way to do it. It's super inefficient. But you can do some caching here. So if your recursive algorithm, let's say it has this fact3, but it does this like 15 times in the run, right? Well, if you cache that result, it means it doesn't have to go all the way back down again. It just goes, oh, I already know what the answer to that is, right? And then it's immediate rather than having to compute it. So there's efficiencies you can gain here, but that's getting more into how computers work and programming than it is the math part, which we'll talk about, of course, but I don't want to put the cart before the horse, But we'll explore this a bit more with some different algorithms. Yeah. So let me just do another example here because this one is pretty trivial, right? I like it. It's something that, sure, we could implement it recursively, and that's kind of fun because you can do this in Python pretty easily, and you get to just see it. You can call this with any number you want that's positive, and it'll work. But again, you don't need this, right? Because how could you compute this normally? Well, you just multiply everything before it together, right? There's nothing there. So another example that I would say is a little more complicated, but not really, is the GCD. So just as a refresher, the GCD, or greatest common divisor, of 2 or more, really, but we're going to focus on 2 here. Numbers. I'm going to say whole numbers. That can be integers. The name kind of tells you what it is, right? It's the greatest divisor that they have in common. Is the greatest divisor the numbers share. So, for example, the GCD of 4 and 6 is 2, right? Because 2 evenly divides both of them. The divisors of 4 are 1, 2, and 4. The divisors of 6 are 1, 2, 3, and 6. The biggest one they have in common is 2, right? Yep.
Are there any alternative names to GCD?
Pardon?
Is there any other way you can see like GCD, like greatest common divisor? Is there any alternative?
This is just I would say for right now, this is the best way to look at it. I would say this is not, how do I say this? This is sort of the basic grade school definition of GCD, I would say. So like when you're working with fractions, like initially, or maybe that's not grade school, that's like early middle school or whatever. But when you're first learning about fractions, you need to care about the GCD so that you can reduce fractions and stuff like that, or find common denominators. So that's usually why it's emphasized. And this would be the definition that's probably given in early school, is just like, hey, look at the numbers and find the biggest thing that divides both of them, right? So the algorithm I'm about to define is probably how I would think about GCD. I wouldn't think about it this is the definition of it mathematically, but it's not how I would think about it. So let's just do a quick example here. I'm going to give myself more space because the idea here is based on that definition and based on what we would know from, say, early school, the way we find GCDs is not very helpful. So, example, let's find the GCD of, I think I have 12 and 42, like that. So we're just going to actually do it. So without any sort of context here, how do we find this GCD? Well, we do it the naive way, right? So naive way, I would say, you list out the divisors of 12 and you list out the divisors of 42 and you take the biggest one. So, hey, it's our old friend Venn diagram. So this is going to be divisors of 12 and this is divisors of 42. And then we just have to think about what are all the divisors. Well, 1, 2, 3, 4, 6, 12. 42, 1, 42, 21, 2, 7, 3, so I guess 14, is 14 work? Yeah. Am I missing anything? 6, maybe? Is that one of them? Yeah, 6 is the one I'm missing. So these are the divisors of 42. And it's a Venn diagram, so we just move the ones they have in common to the middle. So they don't have.
You have 6.
Yeah, they have 6 in common. So what's the biggest one? 6. So the GCD here, all right, it's 6, right? Perfect. Okay, so Now, find the GCD of 1, 2, 6, 3, 5, 1, 2, 6, 5, 3, and 1, 8, 9, 3, 2, 1, 4, 2, 1. All right, so now list out all the divisors of this thing, and list out all the divisors of this thing, and then put them in the Venn diagram, and then find the biggest one, right? No, obviously not. That's ridiculous, right? So, naive method doesn't work. Especially funny if, I don't think it'll be the case because these are big enough that it's very unlikely, but if one of those is prime, good luck finding that out, right? If it's prime, then the only divisors are 1 in itself, in which case you just went on a wild goose chase to see if you could find divisors of it, and there aren't any, right? So that would be horrible. So we want a better way, right? There's got to be a better way to do this. And of course there is, thankfully. So let's find a better way. And if you learned this algorithm, this is probably the way that you actually thought about GCDs. So this is the actual mathematical definition of what a GCD is, but it doesn't tell you how to find them, right? Because if this is our definition of GCDs, then how do we find them? This is the only way we know how to find them based on the definition, then it kind of sucks, right? So what we want is what's called the Euclidean algorithm. I don't remember when it was discovered, but Euclid was the one who discovered it. So he was a mathematician in Greece, maybe, Germany, who knows. And the proof of why this works is not enlightening. It requires you to understand the division algorithm for integers, which means knowing about remainders and that sort of stuff, and some properties of them, and it's just not worth exploring. So we're just going to actually write down the definition of the Euclidean algorithm. So it's recursive. So if we have two numbers, A and B, and it actually doesn't matter anything about them. They can be -2. Who cares? It's fine. So we have our base case. So that's the GCD of A and 0 is A. So this is our base case, right? This is, hey, if we reach this case, we're done, right? We build that massive stack, and then we unpack it upwards to get our actual answer. So then we need our recursive case, and this one is, so I wouldn't expect anyone to actually, figure this out, because again, Euclid was the one who discovered it, and I want to make sure I read it. The remainder of A divided by B. So there's a better symbol for that, right? So GCD of B, comma, does anyone know what the operator for the remainder of A divided by B would be? It may or may not have been covered in Python yet, so if you don't know it, that's fine. Which? Yes, modulo. So it is A percent B. So this is the modulo operator, which gives you the remainder of the integer well, it's not the integer division. I guess it is because it's a remainder. But A divided by B, what's the remainder of that, right? And it will spit that out. I don't know what happens if you use non-integer inputs, because why would you do that? So the point is, this is, again, another convenient way to implement it in Python. Another example of why recursive algorithms are kind of convenient and nice. Because how do I implement this in Python? Almost exactly the same as that factorial we did, except I'm going to call it GCD. The base case is a little different, and the recursive call is a little different. But it otherwise looks exactly the same, right? But let's go through this algorithm, and first of all, it's probably worth confirming that it matches this, right? This is always a good test case, especially when you're writing your own implementations of algorithms. Is okay, work it out either on paper or like with like a simple piece of code to get a known result, right? So like in this case, we just went through with the naive definition and a naive method to find GCD of 12 and 42, right? So this algorithm better spit out 6 or it's not correct, right? And this is very useful when you're implementing your own algorithms. Run it for a test case, and then when you've finished your algorithm, run it for that same test case. They better agree. If they don't, you already have a problem, right? If they do match, then you need more sophisticated test cases, but it's a good idea to start with something really simple, right? So let's go ahead and work through this. So we want to do GCD of 12 and 42. Okay, so let me kind of erase this real quick, and I'll write it in a bit more pseudocode way. GCD of A comma B. Right, so we're plugging in a first number and a second number, and this is what we expect to have happen. So we're plugging in 12 and 42. So are we in the base case? So what is this base case looking for? What do we need to have happen if we want to be in this case? Yeah, right? The second number needs to be 0. So we're asking ourselves, is the second number 0? No. So we're not in this case. So that means we're in this case. So we do the recursive. So what does that mean? So all it does is the second number becomes the first number. So in this case, we're going to look at GCD of 42. And the remainder of A divided by B. So in this case, A is the first number. So of the first number divided by the second number. So what is the first number divided by the second number? 12 divided by 42. That's a fraction that's less than 1. So what's the remainder of that? It's 12. 12 divided by 42 is 0 with remainder 12. So you can plug this into your calculator or into Python or whatever. So this answers another question, is does it matter what order I put the numbers in? No, because the algorithm will correct for that. So it assumes, or it works when the first number is bigger than the second one, but if you don't do that, then the first step just switches them anyway and it fixes itself. So you will always end up with, the first number being bigger and the second number being smaller. And now, let's do it again. Well, we're in the same position. The second number is not 0, but we're going to do the same thing. GCD of 12, comma, 42 modulo 12. So we need 42 divided by 12. What's the remainder of that? So 12, 24, 36, and then 42, there's 6 remaining. So again, this is just doing the mental arithmetic on finding this remainder, but you can plug that exactly into Python, right? 42% 12 will give you 6. All right, so now we look at it, and we say, all right, are we in this case? Are we in the base case? Nope. Second number still isn't 0, right? So, okay, that means we're in this case. So this is GCD of that second number becomes the first number. And then we need to do 12 modulo 6. So 12 divided by 6, what's the remainder of that? There's no remainder, because that evenly divides. And now, aha! Are we in the base case? Yes, the second number is now 0. So what is the answer? It's the first number. And now, so we're done. So in the example of the factorial example, this one's kind of funny because it does actually do the same exact thing. So what it's going to do is it's going to say, okay, I want this. In order to find this, I need to call myself on this version, right? And then to find this, I need to figure out what this is. In order to find this, I need to figure out what this is, and so on. And then it gets to here and it says, oh, this thing is 6, which means now I know the answer to this thing, which means now I know the answer to this thing, and so on, and it builds up, and it's like, that's the answer, 6, right? So it still builds that same kind of what's called a stack, right? It's saying, okay, I need to know GCD of 12 and 42. In order to answer that question, I need to know the answer of GCD of 42, 12. For that question, I need GCD of 12 and 6. And for that question, I need to know GCD of 6 and 0. I know that answer, it's 6. So it goes down these arrows, and then it says, this is 6. Hey, guess what? That's also 6. They're all 6, all the way up, right? It's the same answer all the way, and then it just gets to the top and it says, okay, it's 6, right? So it unpacks it going up in this case, but it doesn't actually do anything, right? Because it's 6 all the way. Once it finds the answer, it just says, yeah, it's that all the way up, right? It just returns the same thing all the way. So in this case, though, well, two things. The kind of interesting thing about this algorithm is big numbers are not actually that scary. So what I mean by that is, well, I'm going to have to grab my phone for this, or someone's going to have to help me. Let's do this, right? Why not? If I just said, hey, we've got this algorithm, let's take a look at this big nasty thing that I wrote down here. But let's see, which one's the bigger one, so we don't have to do the swap. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so it is in the right order. So we're going to find the GCD using this algorithm of 1, 2, 6, 3, 5, 1, 2, 6, 5, 3, 1, 8, 9, 3, 2, 1, 4, 2, 1.
It's literally just 1.
Well, yeah, most things are going to be 1 because the GCD being 1 means they have no common divisors, which is what we call coprime, which is a very important concept in mathematics. But let's just see how many steps this take, though. So the algorithm says, okay, take this other big number, 1, 8, 9, 3, 2, 1, 4, 2, 1, and replace the second number with that first number modulo the second number. I'm going to have to pull up my, I don't know if the default calculator has a modulo operator. It doesn't. So 1, 2, 6, 3, 5, 1, 2, 6, 5, 3, divided by 1, 8, 9, 3, 2, 1, 4, 2, 2, 1. Okay. 6 minus 6 times. Okay, it's another big number, but 1, 2, 7, 5, 8, 4, 1, 2, 7. All right. So okay, fine. Now same thing. This number comes over here. 5, 8, 4, 1, 2, 7. And now it's this thing divided by that thing, or that thing modulo that. So 1, 8, 9, 3, 2, 1, 4, 2, 1. I'm not doing anything fancy here. I'm just plugging this crap into my calculator. 1, 2, 7, 5, 8, 4, 1, 2, 7. All right, that's the remainder, so it's going to be minus that. This is taking longer than I anticipated, unfortunately. 6, 1, 7, 3, 7, 2, 9, 4. And then so on and so forth. The point is, it doesn't actually take that long. These are really, really big numbers. I wrote way too big of numbers. But you can kind of see here, it's happening. This number is shrinking pretty rapidly, right? Like it's half as big, basically. And what's going to happen here, this number is going to get even smaller, right? This probably only fits in once. So then it's going to be GCD. I wish I had a modulo operator on my calculator. 6, 1, 7, 3, 7, 2, 9, 4. And then it's going to be something like close to this, right? Or a little smaller. And then it's going to get even smaller, right? It's going to be 50 something. And then it's going to get smaller and smaller and smaller pretty quickly. So this algorithm probably takes like 10 steps, right? For these ludicrously large numbers. So in general, this algorithm is pretty fast. So even with these really, really big numbers, we can find out this GCD very quickly. Well, why would we want to do that? Two things. One, it being 1 is actually the most common outcome. So we want fast GCDs for a couple of reasons. It being 1 means the numbers are what are called coprime. And what does that kind of mean? Well, a prime number has only 2 divisors, 1 and itself, right? This is kind of the same thing, but for 2 numbers now. So what this is saying is if this GCD is 1, that means the answer to the question, what is the largest number that evenly divides both of these numbers, is 1. That means nothing evenly divides either of them, right? They share nothing in common. So like you can't divide them both by 2 or something like that. If they're both in, say, a fraction, like one of them's the numerator and one's the denominator, it's in reduced form. You can't get any smaller, right? That is what it is. So that's just a basic example of coprime, why we would care about it. It means the fraction is in reduced form. You can't get any smaller than that. But coprime numbers behave a lot like prime numbers. There's a lot of similarity between prime numbers and like a prime number and 2 numbers being coprime in mathematics. They share a lot of similar properties and they behave very similarly. So this is an important idea, which naturally, because of this name, someone might say, hey, well, can we somehow use the GCD to find out a number is prime? No. You can't find out if a number is prime using the GCD. Well, you could if you found the GCD of this number with every preceding number, but at that point you might as well just check the factors, then you haven't saved any time, right? You've actually made it take longer. So this isn't useful for finding out if a number is prime, but it is still a powerful thing. And sadly, more common outcome. So this is why it's kind of funny. It's that thing where if numbers aren't coprime, so they have common divisors, a lot of algorithms that depend on this break. So you really do want them to be coprime. And if they're not, you can easily divide by the GCD, and now they are, right? Because then they have nothing in common anymore. But it's the most common outcome. Just think. The likelihood of something that's even sharing no divisors with something that's odd is much higher because now half of the numbers have been removed, right? Because they don't share 2 in common, right? So literally half the numbers are gone from the pool. So if you just pick 2 random numbers, there's a good chance that they're coprime, right? That they're not going to share any divisors. So it is the most common outcome, and the reason why I say that's sad is because it means you go through this whole rigmarole and you do all this work to see if something is, what's the GCD of these 2 things, and it's probably 1, right? That's probably the answer. But if it's not 1, you need to know that information in any algorithm that cares about these things. So we can also implement this very easily in Python. So I'll erase this and write it again, because if I'm just going to slightly modify it, I don't think it's fair to make you write it. So we could just say def GCD of A comma B. Okay, so this is going to be our GCD algorithm. If B is 0, what do? We return A. If it's not, then we just do exactly what the recursive step said, right? Which said, okay, return the GCD of B and A%B. That's literally it. There we go. That's the GCD algorithm in Python, right? So again, you're starting to see why hopefully recursive definitions can be helpful, right? There is a way to do this non-recursively, and it kind of requires you to know, well, actually it doesn't. You could just do this and just do a loop, right? You could do a while loop until this is the second number is 0, right? You just swap them, and then there you go. You've got an iterative definition of it. But you can kind of see that the way we defined this function, the mathematical process, lent itself to being implemented in programming almost trivially, right? And so that's why people like recursive algorithms in programming, because if you define a process, like a business rule or something like that, some work you need to do, in a recursive way, it is like super easy to implement. Again, with all the potential problems with it. So it's useful to just sort of know recursion. And we're going to talk about quite a few different examples of it for what it's worth. I'm not just going to leave you high and dry with only one, and then, you know, or rather, not with only one, but like these recursive algorithms are very simple, right? They're almost trivial to do. So let me see, I think I have an example here. There it is. So let's do a slightly more complicated one. Which is, so it's more complicated, but I would also say it's trivial in the sense that nobody cares about it. It's invented to be an example in class, really. But it sort of lets us look at what recursion is in a bit more detail. And it gives us a slightly more complicated terminating condition and stuff to do. So we're going to define a function as follows. F of n comma m. So just like the GCD, it's taking two numbers. It has a first number and a second number. So what are we going to do? Well, if the second number is 0, we're going to say it's minus 1. If the two numbers are equal to each other, that's what this means, we're going to say it's 2. So when you see n comma n, that's saying that they're equal to each other, right? They're the same number. So 2 comma 2, we would say it's 2. 3 comma 3, it's 2. Okay, now what do we do to shrink the problem? N comma m, hopefully I have enough space to write this. So it's 3 times f of n minus 1, m minus 1. So we're shrinking both of the numbers by 1. Minus 2 times n minus 1 and m. And then, so we call the function again, but only shrink the first number by 1. So let's find f of 3 comma 2. So the reason why I chose this example is it lets us actually show, you know, sort of the branching paths that like you can build in a computer, or well, you don't build it, the computer just does it. So the way it would call this function, because this is a recursive function that sort of refers to itself twice, right? So it's going to behave differently. And it lets me kind of show that computers are not smart about this, unless you force them to be. So we're going to look for f of, I'm going to use different colors here, I don't need this anymore. So we're going to look for f of 3 comma 2. So 3 comma 2. So we have to ask ourselves, are we in this first case? No, because we need the second number to be 0, which it isn't. Are we in the second case? Right, because the numbers aren't equal to each other. So that means we're in this third case, and all we do is we say, okay, we just do this, right? So it's going to say, okay, it's 3 times f of, well, now we have to do something. We take the first number and subtract 1. So 3 minus 1 and 2 minus 1. Minus 1 minus 1. Minus 2 times f of, and again, I'm going to color code it. So it's the first number, 3 minus 1, and just the second number, not minus 1. Like that. Right, so I've color coded the numbers. Those are the inputs that we're caring about, right? So what does this actually boil down to? 3 of f 2 comma 1 minus 2 f 2 comma 2. So now we actually have two things we need to do, right? We've got this and we've got this, right? We need to figure out both of those things. And this, unfortunately, is what your computer would do. It would evaluate it left to right. So it's going to do this one first. It's going to say, all right, I'm going to go through all of this process and I'll figure this out. And then it will come to here and say, okay, now I'm going to go down this process and figure this one out too, right? And then it will keep branching like that. So let's go to this one. What does this say? Well, we need to figure out what is f of 2 comma 1. And again, I'll stick with the color coding a little bit. So we've got 2, comma 1. So, okay, we ask ourselves, are we in the first case? No, because the second number isn't 0. Are we in the second case? No, because they're not the same thing. So we're going to call this. So this is going to be 3 times f of 2 minus 1 and 1 minus 1 minus 2 times f of 2 minus 1 and 1, like that. Okay, so now we simplify this. 3 times f of 1 comma 0 minus 2 times f of 1 comma 1. Now again, what's your computer going to do? It's going to look at this, go, oh, we got 2 more function calls. Time to break them up, right? Do them left to right. What's this? So we need f of 1 comma 0. Are we in this first case?
Yes.
Yes, we are, because the second number is 0. So we immediately go minus 1. Now, what our computer is going to do is it's going to say, oh, this thing is minus 1. So we go back up here and replace this with minus 1, right? Because now it knows what that is, right? It's saying, we went all the way down this function call stack. We got minus 1, so we're going to replace our call with the known value, right? We know it's minus 1 now, so let's go ahead and plug that in. Now, we go to the next function call on the stack, and we say, okay, we got to do this one. We got to do f of 1 comma 1. Are we in this case?
No.
Are we in this case?
Yes.
Yes, because these two numbers are the same thing, 1 and 1, so we're going to spit out 2. So your computer goes, okay, now I know the answer to this. It's 2. So all told, it's going to take a look at this whole thing here, and it's going to say, well, this thing is 3 times that minus 1 we just found here, right? I'm going to make these green, I guess. I'm trying to color code it so it's not a total nightmare, but. Now minus 2 times that number there, which your computer found was 2. So all told, this is minus 3, minus 4, so minus 7. All right. So that means the answer to this question right here is minus 7, right? And now your computer says, aha, now I know the answer to this question. So I can go back up, cross this out, it's minus 7, right? So it's sort of unpacking itself and then repacking it by going back up the stack. Now we know the answer to this question, so it goes, hey, guess what? Now we have to go do this one. So f of 2 comma 2. No, yes. We're in this case. So it's just 2. So we go, okay, cool. Cross this out, that's 2. So then, what is this thing? It's 3 times minus 7 times minus 7. And then we've got minus 2 times 2 again. So then now we actually have to crunch this number. So it's minus 21 minus 4 is minus 25. So then that means this whole thing is minus 25. So that should be the actual answer to the question for the recursive calls. But this sort of illustrates what I mean here on what's going on in the background. Yep. Yep.
This whole function.
Yep.
Isn't it like? Didn't you just give you the exact same thing every single time? If at the end of the day, you're always going to reduce it to either minus 1 or 2. It's always give you the same thing.
Well, it's going to depend on what the numbers you entered in, right?
Like, I mean, if it was like maybe 7 and 6.
Yeah.
At the end of the day, if you reduce like, if you keep doing 7 minus 1, 6 minus 1, it will lead you back to the same until you get to like.
I think you were confusing. So this is a very common mistake. We are not doing 3 minus 1. We are doing f of 3 minus 1 and 2 minus 1, right? We are calling a function with new inputs. We are not reducing numbers. We are reducing the size of the problem. Don't confuse f of 3 minus 1 and 2 minus 1 with 3 minus 1 and 2 minus 1. These are not the same thing, right? This is a function call. This is just numbers, right? It is not this, it is this. So every step of the way is going to depend on the numbers that you are plugging in, because at every step of the way, if the second number is not 0 and the numbers aren't the same thing, you have to break the problem down even further, right? So you are going to have to build this tree for every single call of this function. That's what your computer is going to do, because in order to figure out f of 3 comma 2, we need to know f of 2 comma 1 and f of 2 comma 2, right? Now, that does lead into something about this, though. I kind of alluded to it. Computers are not very smart. They're not very good at this, generally speaking. If there's not some obvious, like this here is sort of a double recursion here. It's calling itself twice with different parameters. Your computer's not going to be too smart about it, right? It's not going to be able to look at it and go, okay, well, I'm going to reduce it in a certain way to make it very iterative or obvious. What it's going to do is it's going to look at this and go be like, okay, well, I got to figure out this first thing on the left, go down this tree, and I have to figure this thing on the right. But what you can do is you can do caching. So if I had bigger numbers here, so like you said, 7 and 6, it's very, very likely that we are probably going to have repeats, right? So at some point, I'm going to compute f of 2 comma 1 multiple times, right? So if we cache that information, we can basically immediately go, oh, it's minus 7. We don't have to do this, right? We save a lot of memory and space. So you can make these more efficient with some extra effort, but this example here is just to show the sort of, the way this function unpacks itself in a computer. Not really, is not a useful function. It doesn't do anything. What does it do? It's minus 25 with these numbers, right? That's all it does. It lets me draw these arrows and explain how a recursive function works inside of a computer, right? How it's going to build the stack. It's what's called the stack. In order to evaluate this function, we need to determine f of 2 comma 1 and f of 2 comma 2. In order to figure out f of 2 comma 1, we need to know the answer to f of 1 comma 0 and f of 1 comma 1. Those are two things we can find the answer of relatively easily. With that information, we can go back to figure out this problem, which we then use to plug into this to solve the bigger problem, and so on. So what recursion is doing is breaking down a larger problem into smaller pieces. Yeah?
So this entire example is you just showing us what the computer is thinking, not how we...
Basically, yeah. So there's...
Do you want us to learn how to do it this way, or is this just you?
Okay. So I will probably make you do one similar question once, but no, because there's value.
So inefficient.
Yeah, it is. This is why we have computers, right? Is so that we don't have to do this, right? But it's important to understand what your computer is doing so that you can understand why and when it's going to be inefficient, right?
So earlier you said computers aren't smart.
That's true.
We're
Yeah.
gonna do it this way.
Yeah.
Why haven't we fixed that yet?
Because in order to answer that question, the computer would need to determine an order in which to evaluate them efficiently so that we don't repeat information.
But they're moving fast enough to do it.
But if you do that, if you spend computational time reorganizing the algorithm to find out the order you do it, or should do it, you've wasted time. So you might have actually lost time by trying to do that. So the answer to that question is that that's up to you as the developer. So lots of algorithms will do that, right? It will take a look at your data and say, I'm going to rearrange this so that it actually runs a little more efficient. Sorting algorithms they do that a lot, where it's like, if you have the worst case data input, you're like, yeah, I'm going to shuffle it around a bit so it's not the worst case, and then it'll perform a little better. So this is that kind of idea, right? Like if you look at this, these calls of numbers here, you might be able. This is where, as a developer, you'd be like, hey, I have to build this recursively. I don't love it because it's going to take up a lot of extra time, right? I have an example where I have you do the Fibonacci sequence recursively, and asking for like the 60th Fibonacci number would take like 200 days or something like that using the recursive algorithm. which is terrible, right? Obviously, that's terrible. So that goes to the idea if you would look at it and you'd be like, okay, well, how can I improve that, right? Well, I could implement some kind of cache or something like that so that it, I see this number cropping up a lot of times, so I'll just pre-populate it with the answer to that, right? And then you're saving time. So understanding that your computer does it this way is what can let you avoid inefficiencies by just being like, okay, it's doing that a lot, I'm gonna pre-populate it, right?
You can either have the program run longer, or you can have more time spent coding for it to run.
And maybe using more space. So that's the trade-off with recursion, right? It's simple to implement, but it takes extra space and potentially more time to reduce the amount of effort you have to put into implementing it. Not always, right? Some things are just obviously iterative and you just do it iterative and that's fine. But if you run into recursive algorithm, that's when you have to ask yourself, okay, am I going to implement it as written? Or am I going to try to figure out a way to not do it this way? Because, well, one, I think everyone looks at this and like, wow, that's a bit confusing. And yeah, it is. That's kind of, understanding recursion is like one of the early roadblocks in programming when you run into it is like, oh, that's a lot. It's overwhelming, right? Just figuring out what the stack is and how your computer is working with it can be overwhelming. But it is something that eventually you're just going to have to tackle. This is a very, like you said, this is an example I constructed just to kind of show you how it works. This is not a useful example otherwise. So when I talk about something like binary search tree algorithms and stuff like that, you'll see how recursion is actually helpful and why it will obviously reduce the size of the problem in a way that you go, okay, I can contextualize, this is the size of the problem, I have made it smaller, right? And it's not just -1 from the number, right? So, yeah.
Basically, so this basically divides smaller pieces.
Yes, that's
So basically, isn't this not technically a divide and conquer algorithm?
all recursive algorithms are divide and conquer. Because they have to be, because if you do not do that, then you will never reach the base case, in which case your algorithm will run infinitely. So anyway, this example here was just meant to, if you found this overwhelming, that's expected, especially for first time seeing recursion. We're gonna do, so the quiz is basically gonna be do this, but now I will help you with it, right? And I'll give you some guidance, and it's just to get familiar with the way a computer unpacks an algorithm like this. You will not have to do this, if you have to do an algorithm like this by hand, I question why. If it's not just, Travis gave you the assignment question where you have to do it and you're sitting like, 6 months from now, you email me like, Travis, I'm trying to do this. I'd be like, what? Yeah, like, just implement it in Python and see what it spits out, right? Like, what? So, I mean, on that note, this thing right here is really easy to implement in Python, right? If this, I mean, the obvious way, right? If m equals 0, return -1, and so on, right? Elif n equals m, return 2, else return this, right? So this naturally works in Python. So you can give it a try and check that we got -25, right? Just make sure that it agrees. But with that, I don't have, so I could start the next topic. But I mean, especially after filling everyone's brain with recursion, I don't know if I want to, because everyone will just be like, whatever, Travis. So the next topic we're going to talk about is graph theory, so the reason why graph theory is interesting and why I talk about this, so I talk about recursion because most graph theory algorithms are recursive. But they're recursive in a natural and sort of obvious way, in that, I mean, you make the problem smaller, right? So, yeah, with that, I suppose, off you go. Yeah, I mean, there's like 10 minutes left in class. I don't want to start the next topic.